Conservation of momentum. Momentum is a commonly used term in sports. A team that has the momentum is on the move, and it is hard to stop the team. In physics, momentum refers to the quantity of motion and inertia that an object has. Since all objects have mass, so if an object is moving, then it has momentum. Hence, the momentum can be defined as mass in motion. It can also be defined as the tendency of an object to keep on moving with the same speed and in the same direction. Momentum associated with the linear motion is also called linear momentum. When two or more cars of equal mass are moving with different velocities, then the car with more velocity has more momentum. Similarly, if two or more vehicles of unequal masses are moving with the same velocity, then the vehicle having more mass has more momentum. This shows that the amount of momentum that an object has depends upon two variables: how much mass is moving and how fast it is moving. Since mass is a scalar quantity and velocity is a vector quantity, therefore momentum is a vector quantity. Its quantum is equal to the product of mass and its velocity, and the direction is the same as the direction of velocity. If a force acts on a car in the same direction as its motion, then the force speeds up the motion of the car and thereby its momentum. On the other hand, when the force acts on the car in the opposite direction, the force slows down the speed of the car and thereby its momentum. We know that whenever the velocity of an object changes, the motion is said to be accelerated motion. Hence, for an accelerated motion, the momentum of the object will also change. Since acceleration is caused only by the net force, same is the case for the change in momentum. For example, when a ball rebounds from a hard surface, the surface exerts a very large force on the ball, and there is a big change in its momentum. Similarly, when we hit a ball, we apply an unbalanced force to the ball that produces a change in its momentum. In order to measure the quantitative effect of force, Newton introduced the concept of momentum. According to the Newton's second law of motion, the time rate of change in momentum of an object is directly proportional to the external force applied on it, and the change in momentum is in the direction of the force. If the initial and the final velocities of an object of mass m are u and v respectively, then the external force depends upon the product of mass of the object and the rate of change in the velocity of the object. Since the value of proportionality constant is unity, So, the applied force is equal to the rate of change in momentum. In other words, force is equal to the product of mass and rate of change in velocity. We know that the acceleration is equal to the time rate of change of velocity. Therefore, force is equal to the product of the mass and the acceleration. This is the commonly known form of Newton's second law of motion, according to which the applied external force is equal to the time rate of change in linear momentum. It can be seen that small force acting over a long period of time can produce the same change in momentum as large force acting for a short period. Therefore, to reduce damages, the stopping time can be increased to a desired level. Since the momentum of an object is equal to the product of the mass of the object and its velocity, therefore the units for momentum can be obtained by multiplying the units of mass and the velocity, that is kilogram meter per second. Change in the momentum of an object is equal to the product of the force on the object and the time interval. Therefore, Newton's second is also a measuring unit of momentum. Let's solve some problems based on linear momentum. A body of mass 5 kg is moving with the velocity of 10 meter per second. Find the momentum of the body. Using the relation for linear momentum, it comes out to be 50 kg meter per second. In the next problem, calculate the velocity of a body if its mass is 10 kg and it has a momentum equal to 50 Newton second. Again, by using the relation for linear momentum, the velocity of the body comes out to be 5 meter per second. One of the most fundamental concepts of physics is the law of conservation of momentum. You must have noticed that when a moving ball strikes a resting ball, most probably the moving ball stops and the resting ball is set into motion. This is due to the law of conservation of momentum, according to which if number of objects are interacting with each other, their total linear momentum remains the same before and after the interaction, provided that there is no external force acting on the system of the objects. We know that the external force acting on a system is equal to the rate of change in momentum. It can be noticed if the external force on the system is 0, the initial and final momentum comes out to be the same. Since the momentum is a vector quantity, therefore the linear momentum is conserved in magnitude and direction both. That is, the direction of the initial and final momentum remains the same. The most frequent application of momentum can be seen when two objects collide and they act as an isolated system. It is well established that when a collision occurs between two objects, total momentum of both the objects remains constant. That is, the total momentum of the two objects before the collision is equal to the total momentum of the two objects after the collision. Let's see an activity using Newton's pendulum. It consists of a series of identical metal balls of the same size, and all the balls are suspended on a metal frame in such a way that they are just touching each other when at rest, as shown. When one ball is pulled away and is allowed to fall, it strikes the next ball of the series and comes to rest, whereas the last ball of the series acquires the same velocity and swings as high as the release height of the first ball. This shows that the balls simply exchange velocities. In other words, the final ball attains the momentum of the first ball. Let's repeat the activity by starting more than one ball in motion as shown. It can be noticed that the same number of balls on the opposite side swing almost as high as the release height. Once again, the balls simply exchange velocities, and the total momentum before the collision is the same as after the collision. Let us see some examples related to the law of conservation of momentum. Let us see a situation of an elastic collision. When a stationary trolley of mass m has an head-on collision with a moving trolley of the same mass, then after the collision, the first one starts moving with the velocity of the second trolley, while the second one comes to rest. That is, their velocity as well as their momentum are interchanged. Further, if both the trolleys are of unequal masses, then after the collision, the velocity of one trolley increases while that of the second decreases, and the total momentum of both the trolleys remains the same. Let us see a situation of an inelastic collision. When a stationary trolley of mass m has a head-on collision with a moving trolley of the same mass, then after the collision, both the trolleys move together with a velocity which is half of the velocity of the second one. Again, their momentum remains the same. Further, if both the trolleys are of unequal masses, then after the collision, both the trolleys move together in such a way that the total momentum of both the trolleys remains constant. Recoil of the cannon in opposite direction is also due to the conservation of momentum. Since the initial momentum of the system is zero, hence the cannon has to move in the opposite direction to conserve the momentum, as can be seen. Since the initial momentum of the system is zero, hence the cannon has to move in the opposite direction to conserve the momentum, as can be seen. Similarly, when a boy jumps out from a boat to the bank of a river, the boat slightly moves away from the bank because the initial total momentum of the boat and the boy is 0. When he jumps out from the boat to the bank, total momentum of the boy and the boat should also remain 0. This is possible only if the boat moves in the opposite direction. In the similar way, the upward motion of a rocket can be explained by the law of conservation of linear momentum. Let's try to solve some problems on the law of conservation of momentum. A field gun of mass 1500 kg fires a shell of mass 15 kg with a velocity of 150 meter per second. Calculate the velocity of the recoil of the gun. Since the initial momentum of the field gun along with the shell is 0, therefore, according to the law of conservation of the momentum, final momentum of the field gun and the shell should also remain 0. That gives the velocity of the field gun equal to 1.5 meter per second, and the negative sign indicates the recoiling of the gun.